Let me start by thanking the organizers, Amir, Ramprasad, and Michael for doing a fabulous job in organizing this workshop and bringing so many of us together at this place. So thank you very much. And also thanks for giving some very nice tutorial talks along with Ankit. Ankit is probably not here. So which has set up the background for this talk, which I'm going to talk about some recent lower bounds using a tool which was introduced by Neeraj Kayal. It's called the shifted partials. So let me start just to refresh your mind with a little bit of a background of what an arithmetic circuit is. If you all know, it's like a layered circuit of plus and multiplication gates and so on. Product gate computes products of polynomials, sum gate computes sums of polynomials, and you also allow field constants on the wires. So the reason for drawing this kind of diagram is because the talk would be primarily on depth 4 circuit, and which is a circuit of this kind. It starts with a product layer which computes monomials, then sums of monomials, then products of polynomials, which are sums of monomials, and then a final sum. So two things associated with the circuit: depth and size. Size means the number of wires, and in this case the depth is 4. And as I said, that it computes a polynomial f, which is a sum of product of qij's, where qij's are sums of monomials. Right, so that's the setup. Right, two other parameters for the circuit. One is the top fan-in, S, which is basically the number of summons here. And the bottom fan-in, which usually for the most part of this talk, I would assume that the bottom fan-in is bounded by some parameter t. And that amounts to saying that the degrees of these qij's are bounded by t. Okay. Right, so this talk would be about lower bounds of this kind of circuits: depth 4 circuit with top fan-in something and bottom fan-in mostly bounded by some parameter t. And throughout this talk, I'll follow the same notation as followed by all the other speakers. Mostly, n is the number of variables, d is the degree of f. Okay, here is the general template for a lower bound, which almost all the speakers spoke about. I'm just repeating this. So the general template of proving a lower bound, or most lower bounds follow this template, is to define a measure, which Amir was referring to as progress measure, Ramprasad as complexity measure, and I think Michael just used measure. So, okay, so whatever was the last term, I just copied it. So it's basically a map from the set of polynomials to reals or naturals, whatever. These are numbers, and which tries to, you define a measure in a way which tries to exploit some weakness of the circuit, right? What kind of weakness? You want to show that this measure, when applied on the circuit, it's somewhat small, and that small is a function of the size of the circuit. On the other hand, you would also like to come up with some hard polynomial and show that the measure applied on some hard polynomial is quite large. And finally, you set some parameters and show that, oh, there's a significant gap between the measure for the circuit and the measure for applied on the polynomial, and that they give some kind of lower bound for the size of the circuit. So we are going to follow the same template. Right, so just to refresh, so recall the space of partial derivative measures. Here's the notation. I would use this notation to denote the set of all kth order partial derivatives of f. Yeah, and for this talk, we're only going to focus on multilinear derivatives. We are not going to derive with the same variable twice. That's all. And another notation, let S be any set of polynomials. By this, I'm going to refer to the vector space spanned by f linear combinations of polynomials in S. Right? So this is a span of the vector space of polynomials spanned by the polynomials in S. Right. The partial derivative measure with respect to this parameter k is defined as the dimension of this vector space, the space of all kth order partial derivatives of f. Okay, and we saw it many times that this is subadditive, and this is one property which comes in quite handy in proving lower bounds, that the measure does not grow, or it grows very slowly as you add more and more polynomials. Yeah, so this is the subadditive property. So if you have any question, just feel free to stop. Right, so let me once again revisit this model, which is kind of a very good test bed for testing lower bound techniques and as well as hitting set techniques. And this is this diagonal depth tree model where you just take powers of linear polynomials and add them up. That's a diagonal depth tree circuit. And it's we saw it before that the partial derivative measure on this circuit, it's less than s. The reason being it's subadditive, and when you take partial derivative for each of the linear forms, it's at most 1, because k is something fixed. You take kth order, you get L power e minus k times some constant. On the other hand, if you take this monomial x1 to x to the n, it's clear that as you take different kth order partial derivatives, you get different monomials, and their span can only have dimension n choose k, which is the number of distinct monomials. Right, so if you choose now, so the final step was to fix the parameter k. If you choose k to be n by 2, you get this nice lower bound of 2 to the n, which is kind of asymptotically optimum because of Fisher's formula. Okay, so, and this is the start of the shifted partial measure, which tries to extend this diagonal depth tree model to the following model and asks us to prove lower bound for this model. Let's say for a moment, if I replace the linear polynomials by quadratic polynomials, degree 2 polynomials, and take the same diagonal structure, it's like a diagonal, special diagonal depth 4 circuit. And how do we prove lower bound for this model? Let's see. Let's focus on a very special case. Well, let's say Q, one of these Q is just this. Yeah? And let me use this notation yi equal to xi plus 1 if I is odd and xi minus 1 if I is even. It basically means that what is the partner of x in this polynomial? Let's say when x1's partner is x2, x2's partner is x1, and so on. Right? So yi is the partner of xi in this polynomial. That's all. Now, if I derive, just focus on one term, which looks like q power e. If I derive once with respect to some variable, its partner comes out, yeah, and with some constant. If I derive it twice, another partner comes out. And remember, we are only focusing on multilinear derivatives. We are not deriving with respect to the same variable twice. Yeah, and it goes on. If you do it k times, I get something. But notice that from the partner itself, I can find out what the derivative is. So there's a unique correspondence between the partner and the derivative, which you can easily formalize and say that this only means that all the kth order partial derivatives of one term, they are all linearly independent. Yeah, because one such derivative looks like this. Now, as you run over different monomials, you get different monomials here. And if you take the linear span of this, it can only be n choose k, right? Because these will be distinct for distinct monomials with respect to which you are deriving. So this is a bit of a problem because for one term itself, I hit the maxima. This is not exploiting any this measure, partial derivative is not exploiting any weakness of this circuit, because I know for any f, I can get at most n choose k. So which means that in this setting, the partial derivative measure as it is, though if you just use it like this, it's unable to distinguish between any power of a quadratic polynomial and any hard polynomial. Okay, and it is at this point that Neeraj introduced this nice augmentation of partial derivative measure. It's called the shifted partial measure. So let me start by defining it. It's basically the same, nearly the same as the partial derivative measure, except that it has one extra augmentation. And let me denote the set of all monomials of degree less than L by this notation, x to the less than L. Yeah, and these two things remain the same as before. Right, so then the shifted partial derivative measure with respect to two parameters, the order of the derivative and the degree of the shift, it's defined as the dimension of this space. Now what do I mean by this space? This space is basically found by polynomials which are kth order derivatives of f, multiply it by a monomial whose degree is at most L, take all such polynomials, take their linear span, and then look at its dimension. Right? That's what this means. So it's a set of all polynomials formed by multiplying a monomial with a derivative. So that's the shifted partial measure, the original shifted partial measure. And let's see how this helps in proving a lower bound for the model we just saw. And one nice property about the shifted partial measure you can take it as a simple exercise, is that this is also subadditive. It doesn't grow, and you can prove it very easily. Okay, but before I go into the model, let's see how large can the shifted partial measure be. Yeah, so let us record the definition here. Now notice that this set, it has at most these many polynomials. It has n choose k many derivatives, because I'm focusing on only multilinear derivatives. And it has a set of all monomials of degree at most L can be at most n plus L choose n. So this product set, it has at most these many polynomials. So the dimension cannot be more than this. On the other hand, if you focus on the degree of any polynomial in this product set, the degree cannot be more than L plus D minus K, because you started with degree D, that's the degree of f. When you took derivative k times, the degree shrunk to D minus K, and then you are adding another degree L. So every such polynomial in this set has degree at most L plus D minus K. And how many such monomials can be there? This much. So you have this many polynomials, all of them degree bounded by this. So, yeah.
Taking a multilinear in the X superscript, at most L.
This?
Are these multilinear?
No, needn't be. Not for this measure. Later on, we'll make it multilinear. But for this, it's just any monomial of degree at most L. Oh. Oh, n choose k is coming from here. This point is multilinear. Okay, so you have these many polynomials, all of them have these many monomials, so the dimension of the set can be only minimum of these two quantities, right? Yeah, so this will turn out to be quite crucial. So this is just the proof of it. Right, so obvious question, can we find a polynomial whose shifted partial is like this? It hits the maxima. We'll see the answer is yes, almost yes, and we'll see this shortly, but let's go back to the circuit first, okay, and see that this measure is indeed exploiting some weakness of the circuit. But since I know that it works, let me extend the circuit further. Let me make it sum of powers of polynomials with not just degree 2, but some degree t, okay, and work it out in terms of t. You can assume t to be 2, okay? Right. So because of subadditivity, I know that this is less than sum of the shifted partials of individual terms. Yeah, so let's focus on one term and see what the shifted partial looks like. And you should spend some time on this observation, yeah, because I didn't have enough space to add the proof. So if you take a derivative of t, let's see what happens. Yeah? So when you take a derivative first time, and it has degree t, so something comes out, and you get something times q power e minus 1, but that something has degree at most t. When you take derivative a second time, something else might come out. So this, when you take derivative k times, these somethings, each of degree t, can only multiply and give you a polynomial of degree at most kt, right? And what you get is a polynomial of degree at most kt times q power e minus k, right? So if you just make this argument a little formal, you'll realize that every derivative is a polynomial of this kind, is a polynomial of degree at most kt times q power e minus k. So naturally, it is just chain rule. If I now apply the shift on both sides, then m times a derivative.
Sorry, but you're assuming that the xi1 doesn't appear with xi2 in the Q, because then otherwise, like...
No, this is true even otherwise.
Even otherwise?
Yeah. Even if like you derive the same element twice, you can take a few q's along with.
But you have like q to the e minus 1 as well.
That's okay. So let's say I first time I derive, I get some q prime times q to the e minus 1. Next time I derive, it might be that I get q double prime times q to the e minus 1. But take one q and merge it with q double prime.
Oh, okay.
Right? So that way. Yeah, I'm taking t because of exactly what he said. So you can merge q.
The q might switch. You need to use the q.
You can take t minus 1.
T minus T minus 1 should also work.
Degree goes down by 1.
Degree goes down by 1, but what he's saying is like, let's say you derive first time, you get q prime times q to the e minus 1. When you derive second time, one term would be q double prime times q to the e minus 1, not e minus 2. But I want e minus 2.
E minus 4.
No, but all you're using here is that any kth order partial derivative is divisible by q bar e minus k.
That's true.
And
That's
the
true.
rest of the thing is going to be of k times t minus 1.
T minus 1, yeah, T minus 1 will also work. Yeah, that will also work, sure.
It's not going to tell you that you're not doing that.
So just coming back to the point everyone is saying is that we can actually do a little better and make it k times t minus 1. Yeah, so this will work. But the setting of parameters we are going to work with, the asymptotics won't change because of this minus 1. Okay, good. So when you multiply with a monomial, then what you get is that it's a polynomial of degree at most L plus kt times q to the e minus k. So which means that if you focus on one term and look at its shifted partial, the dimension is basically coming from this part, right? And how many? What if you look at the set of all polynomials of degree at most L plus kt, its dimension can be at most this, right? It's exactly the number of monomials of degree L plus kt. So for one single term, I know it's bounded by this. Yeah, good. I got a good upper bound, and I know that in the best case, I can get a good lower bound for some random polynomial. Yeah, we'll find an explicit polynomial later on. Yes. Yeah.
G1 times f and G2 times f.
Yeah.
And the span of these two polynomials, is it the same as the span of G1 comma G2?
Yeah, because the f part is common, right? Any linear combination, f linear combination would look like a constant times G1 times f plus a constant times G2 times f, and then you take f common. So it's basically a linear combination of G1 times G2 times f.
Is a polynomial.
Yeah, f is a polynomial, so you can take that common, right? Out.
I'll do it as homework.
Okay, thanks. So, right, so we got a good upper bound here. So, any other question? Okay. So now if you apply the subadditivity, we get the shifted partial for the whole circuit is bounded by s times the shifted partial of a single term. So, good. So we know, let's record this here, that for the whole circuit, I got a good upper bound. And for a hypothetical hard polynomial, I get something like this. Yeah, and you assume that such a polynomial exists. And let's proceed. Okay, if I proceed, what do I get? The best lower bound on the top fan-in I get is something like this. It looks like a very messy ratio. And I'm yet to do the last step of setting the parameters k and l. And from this ratio, apparently it's a bit scary to start with. So this is the last step. And let me just briefly spend a couple of slides on how to choose parameters. Yeah. So there are these two ratios basically. This by this and this by this. Yeah, there are these two ratios. Let's give it two different names. Let's call the first ratio R1 and the second ratio R2. And let's get some idea about how to choose K and L. Look, for R2 to be greater than 1, I must choose KT, which is less than D, right? At least, or D minus K, right? So I want KT to be less than D minus K for R2 to mean something, to give me at least some non-trivial lower bound, right? So what I do is like, okay, let my K be some small constant. Not always this is a constant, but yeah, for most lower bounds, this is a very small constant, times D by T. That's how you choose K. Yeah, you fix the constant later on, till at the very end. Now, how do I choose L? Now, it turns out, if you fix K like this and look at this two ratio R1 and R2, it behaves like this. R2, it starts very high, and as L grows, it starts decreasing. Whereas R1, it starts increasing. Yeah, and remember that what I get is always the minimum, right? So natural choice of L would be this point, right? So if I choose L here, I would be getting a lower bound here, right? Which is R1. If I choose L here, I'll be getting a lower bound here, which is R2. And this is the maximum, right? So you choose L, there's a sweet point. Let's call that L star. It looks like this, but ignore this term. Yeah. So let's call that L star in terms of N, D, and K. And once you do this, you just fix it. Yeah? If you fix this, so this is how you choose K and L. And once you fix this, if you work out these two ratios, they become the same exactly by this graph. Yeah? And you get something very nice. The ratio becomes like n choose K. And this delta is the same delta here. Yeah? So you get something like n choose K to the 1 minus delta. Okay? Which, because K, I chose it like this, it gives like nt by d to the d by t. Right? Just plug in the value of K. Right, so that's the kind of lower bound we get on the top fanning. It's roughly n to the d by t, if n is also polynomial in D. Right? Okay, now why did I use the term best? Yeah. Why? I mean, I know the best shifted partial derivative of a polynomial would be one of these two terms, the minimum. But what about this upper bound? I mean, we did apparently some kind of a very simple calculation to get the upper bound for the circuit. Is it possible to get even smaller upper bound for the circuit so that the ratio gets even bigger? It's possible, right? I mean, it's not clear because we just found out one upper bound. Now, it turns out that because of this very nice work by Fournier, Limay, Malod, and Srinivasan, that actually the upper bound is tight. We'll see this later. I'll come back to this. So believe me at this point that this upper bound that you're getting is also tight. Right? So this is the best top fan-in lower bound you can get via this original shifted partial measure. Okay? Right. So the only thing that remains is to actually tell you some explicit hard polynomial which achieves this minimum of these two, the best possible. But before I get into it, I'd like to do two things. First, I would like to make the circuit a little more stronger. Just one slide, bear with me. And then I'd like to give you some intuition as to why the shifted partial worked. Yeah, some geometric intuition. And then in the end, I'll come back to the polynomial, the explicit polynomial. Okay, so let's try to make the model a little more general. And now the general model is this. And this is the model which many of the speakers covered in the depth reduction result. And the model is like this. It's a depth 4 circuit where each of these QIs has degree bounded by T. Okay? And there's a depth reduction result which shows that if you prove strong enough lower bound for this model, you prove VP not equal to VNP. And that's the only motivation why I'm trying to extend this, the diagonal depth 4 kind of model to this kind of model. Yeah, and just one line, it just follows directly from Fisher. But notice that because I assume that C is homogeneous, because that's the kind of circuit we were getting in the depth reduction result, I can also assume that M is like D by T, because each of them has degree T, roughly, and total degree cannot exceed D, right? So the number of terms that you get is like D by T, right? Okay. Right, so yeah, so this is the notation that I'm going to follow from here on. I'm going to call this kind of circuit as homogeneous depth 4 circuit with bottom fan-in, the last degree of the Q's, bounded by T. Okay? Right, so why is this one line? Because of Fisher's formula. I mean, we saw this before. Every term, you treat it as a monomial. Just monomial, just one single monomial in Q1 through Qm. And use Fisher's formula to convert it into sum of powers of degree at most T polynomials. But for each of them, you will get a blow-up of roughly 2 to the m, right? If you apply Fisher's formula. And so if you do this for all S, you get something like, a model which we just covered, diagonal depth 4, with each of them degree at most T, where the top fan-in increased by a factor of 2 to the m. This might look too big. This is indeed big. M is like D by T. But because of the lower bound that we saw, it is like n to the d by t. If you remember the lower bound, it's like n to the d by t. Now n to the d by t is much higher than d2 to the d by t. So this small increase won't matter. Yeah. So let's see. Yeah, I just told you this. Yeah. So observe that it's because of this that n to the d by t is larger than 2 to the d by t. Any lower bound on this model automatically of the kind n to the d by t automatically implies the same lower bound asymptotically for this kind of circuit. right? Just one-step application of Fisher. Is this point clear? Yeah? Okay, good. Right, so now this looks temptingly close, although it's not. It looks temptingly close because what we have is like an n by d to the d by t kind of lower bound. And we know from the depth reduction results that if you can increase the asymptotic here, if you can prove n to the small omega of d by t lower bound, then you get Vp not equal to Vnp. Yeah? For any t less than root t. Okay? Right. So, and this is the threshold. I mean, that was the reason I used the word threshold in the title. And that if you cross the threshold, you'll get a Gödel prize. Okay. So, right. So now you compare these two terms. That's what I was trying to say in the last slide. That what we get is this, and what we want is this. Yeah. So that's all. Let's remember this. Right. So now let me give you some intuition as to why shifted partial worked for this kind of strange-looking model, which is kind of the general model at depth 4. So some geometric insight. Okay. So please stop me if you want to ask me any question. Okay. So I'll try to define ideals and varieties. So let G1 through Gm be some polynomials over complex numbers. Let's say x1 through xn. Yeah. So and I be the ideal generated by G1 through Gm. Okay. And V be the set of all common roots of G1 through Gm. Okay. Now, intuitively, the more number of polynomials you add, the set of common zeros will shrink, right? So there's kind of an inverse relationship between the size of the variety, whatever I mean by size, and the size of the ideal, right? So in the sense that the larger the variety, the smaller the ideal. Okay. Now, why does this kind of insight help in our case? We'll see, but I would also like to make a little precise what do I mean by a variety being large or an ideal being small. So the way this is measured, the size of a variety, let's say, is through its dimension. Yeah? There's something called the dimension of a variety. Let's say a plane has dimension 2, a line has dimension 1, let's say a cube-looking structure has dimension 3, and so on. Okay, so why does it help? Let's see. So for a moment, assume that your G1 through Gm are all kth ordered derivatives of a single term. A single term looks like q to the e, right? So I want to understand why is the shifted partial small for this. So these are all derivatives, and I is the ideal generated by this. And V is the variety of this ideal, the set of common zeros. Now notice that every polynomial in the ideal is divisible by q to the e minus k, because after you take derivatives k times, you have q to the e minus k as a common factor, which means that every polynomial in the ideal is divisible by q, and that's why the variety of q, the common zeros, the roots of q, are common zeros of all polynomials. I mean, all the G1 through Gm. So any root of q is also root of any Gi, right? But how large is the variety of q? Now, q is just one homogeneous polynomial, and it is known that by some nice results that if you add one homogeneous polynomial and look at its dimension, the dimension of the variety, it's quite large. The dimension is n minus 1, right? N minus 1 dimension is like sort of the whole space except like one dimension missing. It's quite large, right? So, and this is the reason why the variety is quite large. But that should also mean that the ideal is small, but I haven't told you what I mean by the ideal to be small. So let me make this term precise by actually giving you some measure of how to capture this smallness of an ideal, and this is done using what is known as the Hilbert function. So let me define it here. So let's call the set of all degree at most L polynomials by over complex numbers by this. Yeah, and for any ideal, let me use this notation to capture the set of all polynomials in the ideal whose degree is bounded by L. Okay, right. So naturally, this is a vector space over C, because if you multiply two polynomials of degree at most L and sum them up, its degree is still at most L. So it's a vector space of over C. Now, Hilbert defined a nice function. So this is the denoted by hi of L, which is basically this quantity, n plus L choose n, which is the set of all monomials of degree at most L, minus the dimension of this. I'm treating I here as a vector space over C, right? So this is something. But there's a very nice theorem which says that this HIL, the behavior of HIL for large enough L, it's basically a polynomial. So I can treat HIL as a polynomial in L. That's how this Hilbert function behaves for sufficiently large L. Okay? And not only that, now when I say that this is a polynomial, it makes sense to talk about the degree of the polynomial. It says that the degree of this Hilbert polynomial is exactly the dimension of the variety of I. Now, okay, I've said a lot of things, but coming back to the point, what does it mean? So let's record this thing, that Hilbert function is this is a polynomial, and it's the degree of the polynomial is exactly dimension of the variety. Yeah?
What is the dimension subscript C of I smaller than n? It's not even an ideal.
Sorry, which one?
Dim Ci at most L.
Yes.
It's not an ideal.
This is not an ideal. This is a vector space. Yeah, this is a vector space. So that's why I'm using the term dimension. Yeah? Okay. So now this is a polynomial, and this is the relation by definition, and the degree of the Hilbert polynomial, it relates to the dimension of the variety like this. If I plug in, just before plugging in, bring dimension this side, take the polynomial this side. Now if I plug in the degree of the entire polynomial, this entire polynomial will look like L to its highest degree plus lower order terms in L, right? I'll just plug in the value of the expression for HL, which is a polynomial. And its degree is exactly dimension of it. And now comes a very nice thing. See that if the dimension of the variety is large, something is small, something related to the ideal is small. Right? And it's close to the shifted partial. And this is what I mean by smallness of the ideal. This quantity basically captures smallness of the ideal. Yeah? And relates to the dimension of the variety. It's in an inverse way. So which means that larger the dimension, which in our case is true. Remember, in our case, the dimension was the roots of Q, and that was n minus 1. Yeah? If the dimension is large, then I get this quantity, dimension of I restricted to degree L is small. What does this mean? This means that if you just look at the shifts of the derivatives, remember I was the ideal, yeah, generated by G1 through Gm, the derivatives. If you look at the shifts, now this is actually contained in this set. If you choose L to be like this, are you following? Right. So the degree of this quantity is at most L plus this is the degree of the derivatives, right? So if you choose L to be capital L to be like this, then this quantity is inside this. So if this is small, this has to be small, right? So and that was the intuition that you expect. And this is basically the shifted partials. And so you expect that to be small. Any question on this? Okay. So, yeah. So you choose L to be this, right? Now if you look at the degree of every polynomial here, what is the degree of the polynomials here? It's a derivative of a term, right? Any term has degree of t, minus this is the loss you incur because of the derivatives. And then you gain L.
How is it in the ideal?
The ideal is how is that? This in the ideal? The ideal is generated by multiplying with polynomials, right?
Oh, okay. What is the generator of the ideal?
G1 through Gm. Okay? Oh, right. So now let us do the last piece of the talk. So any questions, just feel free to stop.
Sorry?
Yeah.
So can you go back to the previous slide, please?
Yes.
So are the G1 to the Gm monomials or?
They are, no, G1 through Gm, they are derivatives of a term. You recall? A term looks like Q to the E.
Okay, so my point is that, I mean, I think that's kind of crucial that those are also like terms of small degree, because, I mean, otherwise, if you multiply monomials with something else, might be that the bigger polynomials are better in a way that you're getting monomials you already have, right? So
but won't that be better, because that will only make the dimension even smaller, right? Such repetition.
yes, that's my point. That
Right.
sometimes, like if you have, like if you already like covered a lot of area, that the dimension will stay smaller, but having like small terms could have a bigger dimension in the end. So,
So you're saying that this might happen, that this is small but this is big? Something like that? I agree with you. There might be some values, as I said, that this is in the asymptotics for large enough L. For large L, it behaves like this. But for small L, this kind of neat relationship doesn't hold. Yeah. So this is just the intuition, as to why this works, and maybe some other tools from algebraic geometry might help. Okay. So now let's focus on the search for hard polynomials which achieves this maximum shifted partial derivatives. Now there are several candidates. We could choose the permanent, which is in VNP, the determinant, which is in this algebraic branching program world. By the way, this is the hierarchy. So you have algebraic branching programs, you have VP, you have VNP on top, one contained in the other. And iterated matrix multiplication, I'm not sure whether anyone of you defined this, but let me just define this polynomial quickly. IMM stands for iterated matrix multiplication. Yeah, so it's basically the polynomial computed by an ABP whose width is W and whose length is D. And every layer, if you just focus on a layer, it's completely full with edges. And all the edges are labeled by a unique variable. Let's say if this is level 1, this is level 2, all the edge from I to j is labeled by a variable x2ij. Yeah, so you have distinct variables all throughout. That's a polynomial. Okay? Okay. Right. So, and there's one more candidate, that's the elementary symmetric polynomial, and as Amir showed on the first day, that this is computed by a very small depth 3 circuit that is at the same time multilinear. So the M stands for multilinear here. Okay, so there are these 4 candidates, and let's see whether we can show that the shifted partial of these polynomials are large or not. The first one was done by Ankit Gupta, Neeraj Khyal, Pritish Kamath, and Ramprasad Saptarishi, and this is sort of among the first 2 papers which dealt with shifted partial and proved some very nice lower bounds, and they proved some lower bound on the shifted partial of these 2 polynomials. Tried to show that the shifted partial of these 2 polynomials are high. So let's see. I'm not going to prove anything, just to give you some kind of a comparison as to how the shifted partial of different polynomials behave. They show that for the determinant, it looks something like this. Don't worry too much about the exact parameters. So for your reference, how do you go? Yeah, let me write down what we want. Recall one of the 2 minimum was this. Yeah, the number of derivatives times the number of monomials. So we are referring this thing, or we are comparing this quantity with this quantity. It is indeed less. It is indeed less because of the loss here mainly. This minus 2k loss, it comes in handy. So naturally, they don't get a n to the d by t lower bound. They get something weaker. They get 2 to the d by t lower bound. Okay. So is this because the calculation is not tight? Not so. They actually came up with a very nice upper bound and showed that actually for the determinant, the shifted partial is not the maximum possible. They showed that it is less than another quantity, and these 2 quantities are reasonably close to each other. Okay. So for the determinant, you can't do better. I mean, it seems like with shifted partial technique, 2 to the d by t is the best. You can. Okay, so determinant done. What about the permanent? Now, I'm not going to show, for the permanent also the same shifted partial thing I showed for the determinant, the same lower bound holds for the permanent also, but not the upper bound. Yeah, so they posed it as an conjecture that the shifted partial of the permanent is actually much larger than the shifted partial of the determinant. Of course, it's still not going to give anything better than n to the d by t, but it might give something like n to the d by t for the permanent, okay? But probably not for the determinant. So this conjecture is still open. Correct me if I'm wrong. So what we did in a follow-up work is, we don't know how to analyze permanent very tightly. So we replaced permanent by this another polynomial, which I'm going to define here. It's called the Nizan-Wigderson polynomial. And for this polynomial, we show that indeed the shifted partial is sort of the maximum you can get. So let's see what we showed. We showed that the shifted partial is greater than, again, some quantity. And just for your reference, if you recall the second term in that minima of two things, the second term was exactly this. This is the number of monomials of degree at most L plus d minus k. Right? So if you compare this, you see that the loss is only inverse polynomial. So it's very close to the optimum possible. And that's why no wonder we got this n to the d by t lower bound for Nizan-Wigderson polynomial with n variables and degree d. Okay? For this kind of circuit. Right, so we might see a proof later if I get enough time towards the end. Right, and what about the iterated matrix multiplication? And this is a highly interesting result. As I was mentioning, this was by Fournier, Limay, Malod, and Srinivasan. And they showed that even for the iterated matrix multiplication polynomial, the shifted partial ignored the exact quantities. Just for your comparison, coming back to the first term of the minima, it's again reasonably close. It's not that close because of the first term. The first term being w to the k. What was w for the iterated matrix multiplication polynomial? It was the width. So if you see the number of variables in IMM polynomial is roughly w squared times d. W squared coming from each level, and there are d such levels, right? So I'm not getting n to the k, which is like this quantity, n choose k. I'm getting w to the k. Yeah, but they show that this is still fine. This loss is not that much, and still showed this n to the d by t lower bound for iterated matrix multiplication. Right. So, So now, and this shows something highly interesting. The reason being, this is the point. This is the point they showed, that you cannot actually improve the upper bound on the shifted partial of the circuit, because if you could, the upper bound on the circuit has got nothing to do with IMM or Nizan-Wigderson or any polynomial. That is on the circuit, right? If you could significantly improve the upper bound, you would have actually gotten a lower bound better than n to the d by t even for IMM, right? But because of the depth reduction results covered initially, we show, we know that for IMM, we have a depth 4 circuit like this, whose size is like n to the order d by t. So we already have a small circuit. You can't show a lower bound more than omega d by t. So that's kind of like really pins down the point that you cannot improve the upper bound for the circuit. Whatever you have by this simple calculation is sort of the best. Is the point clear? Yeah? Okay. Right. So I'm done. So what about the elementary symmetric polynomial? You remember that it's right there in the depth 3 circuit. It's not homogeneous, but it's multilinear. But it's quite simple. So this was analyzed by Pritesh, and later on by another paper by Fournier, Limaye. Instead of Malo, that we have Mahajan here, Meena Mahajan and Srinivasan, 2015. And they analyzed the shifted partial of the elementary symmetric polynomial and showed that in certain regime of parameters, it's fairly large. But I would still say that this is sort of an open end. We still do not understand the shifted partial of symmetric polynomials that well. Okay. The reason being, they show that when d is really small in terms of n, then it is very large. Now, it could be a proof artifact, or I don't know why it's like that, but it looks unnatural. Why should it be? I mean, for larger d should only make symmetric polynomial harder. So you would expect the shifted partial to be large even for larger d. So yeah. So having said this, so it's kind of a slightly open end here. We do not quite understand. So, right, so let's get back to the shifted partial of Nizan-Wigderson polynomial, and let me try to bore you. Do I have 5-7 minutes or 5 to 7 minutes. How much time do I have? 5 minutes. Okay, right. So let me do a little bit of the analysis of the shifted partials of a Nisan-Wigderson polynomial. If not anything, let me just give you just the definition of a Nisan-Wigderson polynomial. So the Nisan-Wigderson polynomial looks like this. It's a sum of monomials. Every variable, it has two coordinates here, I, comma, something strange here. And how many variables are there in one monomial? D of them. Now let's come back to this second coordinate. What is H? Now H is a univariate polynomial over some finite field fd. This d is the same as this d, the degree. Assume that d is a prime, let's say, so that finite fields make sense. And H is a univariate polynomial with degree at most k. Right? So what you are doing is you are summing over all univariate polynomials of degree at most k, and then every monomial stands for a univariate polynomial. It's just the evaluations of the univariate polynomials at that first d points. So basically I'm identifying the elements of fd with 1 to d, that's all. So when I say h of I, I'm evaluating the univariate polynomial at I. I is treated as an element of the finite field. How many monomials are there? Exactly the number of univariate polynomials of degree at most k, which is d power k. Every monomial stands for a univariate polynomial. That's the point. Yeah? And how many variables are there? D square. Because you fix this in d ways, and no matter what you fix here, you will have a univariate polynomial whose evaluation would be that. Right? So, because you have plenty of freedom here. Okay. So you have d square variables of degree d, d to the k terms. Actually, I should have introduced a parameter k also, because k is used to define the Nisan-Wigderson polynomial. But I took it away deliberately just to keep the notation simple. Right? So k is used to, is used to fix the degree here of the univariate polynomial. Okay, so that's how a Nisan-Wigderson polynomial looks like. But one single property which actually helps us prove a lot of subsequent lower bounds, and that is this one crucial property of this polynomial, that if you take any two distinct monomials, they are almost disjoint. Their overlap is only on k, at most k coordinates. Yeah, so two distinct monomials of this share at most k minus 1 variables. That is, the distance is at least d minus k, roughly. Why do they share at most k minus 1? Because of this univariate polynomial. Right? If two distinct monomial meaning two distinct univariate polynomials I'm dealing with. And two distinct univariate polynomials, at how many places can their evaluations be same if their degree is at most k? It can be at most k. Right? So, and this is one single point which really helps in a lot of lower bound proofs later on. It's called the disjointness property. Now, since I have 3 more minutes, okay, or maybe 2 more minutes. Okay, so sorry, 3 something. Okay, so let me just give you a glimpse of the analysis in 3 more minutes. And this is actually taken from Suryajit Chilara, who is unfortunately not well, and Partha Mukhopadhyay. And this analysis would be also inspired by the Fournier, Limay, Malod, and Srinivasan paper. Oops, what happened? Something is missing. Oh, that's strange. Okay, so you focus on certain kinds of derivatives, not all derivatives, certain kinds of derivatives of order k, which are of this kind. You derive with respect to x1 something, then x2 something, then xk something. Yeah? So you have this set of derivative operators, and you apply on Nisan-Wigderson, and you get these polynomials. Right? Notice one thing, that this set is a set of monomials. The reason being, if you derive by this multilinear monomial, you cannot get two monomials which has the same this part common, because they share only k minus 1 variables. So if you derive, either your derivative is 0 or you get only one monomial. Right? You can easily show that the derivative won't be 0 because I'm just deriving with respect to k terms. There will be one univariate polynomial which will give a monomial. So the point is, which makes the analysis quite simple, is that this particular subset of derivatives gives you just a set of monomials. And a set of monomials are relatively easy to analyze under shifts. Okay, we haven't added shifts yet. So you get how many, the size of this is exactly the size of the number of derivative operators, which is d to the k. Right, so this is a set of all monomials, d to the k, and pairwise they are quite far from each other. Right, so they share very few variables. So as I said, like since this is a space of monomials, when you apply a shift to this, and you want to count the dimension of this space, but this space is spanned by mostly monomials, all monomials, that's all. So if it is spanned by monomials, you just count how many distinct monomials are there in the set when you absorb the shift inside. And that will give you a lower bound on the dimension of the space. Right? If the space has, if my set of polynomial has distinct k L monomials, then its dimension has got to be at least L, right? So that's the point. So you just count the number of distinct monomials in the union of these sets. You call the sets different, name them differently. And one single set is very easy to analyze. One single set is just the number of shifts. You change the shift, you will get a different monomial. Right? So it's the number of shifts is just 1 plus L choose n. So the first term, so it's the union of these monomial sets, and I apply inclusion-exclusion principle, I get the size of this set to be, it should be a greater than equal to sign. This is not equality, greater than equal to this, like just inclusion-exclusion. But the first component, the first sum, and I have a very good idea. This is just, each one of them is n plus L choose n, and there are d to the k of them. And it is here, analyzing this term, where the disjointness property helps. So I won't go into the detail of it, but one can actually use the disjointness property to show, to upper bound this error term that you get, and show that this is actually small, this is compared to the first term. This is less than half the first term. So that overall, you still get something close to this. Now, are we doing good? Almost. Now, if you recall, so let me just refresh your mind. The first term in the minima was n choose k times n plus L choose n. What we have shown here is the shifted partial of the Nizan-Wigderson is at least d to the k times this. The second term is fine. The first term, I should have obtained n to the k, roughly, but what I have is like d to the k. But n and d are polynomially related. So that's why we are still good. Yeah. So, and this is like still close. This is still not the best possible analysis, but simpler analysis. So this is still close to what we have in mind. Okay? And yeah, so forget the details of the analysis. Forget the details. And that's the end of the proof. You can see the top part of QED here. Okay, so it's the end of the proof. Okay, so we get what we want. And right, so let me end with a few questions. It's just one slide. Okay, I'll just end. So what I have told you, it already showed one limitation of the shifted partial measure, that it can touch n to the d by t, but it can't do better, right? But n to the d by t for a non-trivial circuit like this is still good. So one would naturally be tempted to ask if one can prove better lower bounds for some questions which are quite interesting. So let me go one by one. One is this Bauer-Strassen lower bound, with Amir covered yesterday or day before maybe, and this is the best known lower bounds for general circuits. If I just ask you to just improve, this lower bound, probably not super polynomial lower bound, but just improve this. Could the shifted partial be useful in improving the state of the affairs here? The second question is this, the best known lower bound for general formulas. I had n to the 1.5 here, but then I asked Amir yesterday, and he corrected me and said, no, n to the 2 is the best lower bound known for general formulas. And again, nothing is known. Maybe shifted partial might help. I don't know. It's worth exploring, perhaps. Third question is the determinantal complexity of the permanent, which is the heart of the determinant versus permanent question, which is the heart of algebraic complexity theory. Again, the best determinantal complexity of the permanent known is omega n squared. Can we do better? N cube, n to the 4, can it give anything better? The reason I'm hopeful is like the proof goes via Hessian and all that, and it's not clear whether one can use shift in a very clever way along with Hessian to improve the lower bound here. Okay, and the fourth one is a quadratic lower bound for general depth 3 circuits, And recently what we found is that these three things are almost open. The fourth one could be improved a little bit, and that would be needed stock later in the workshop. Let me just quickly, the first one is I don't know, I have any idea. Don't have any idea. The second one, at least for some class of formulas, those are called regular formulas, we could show super polynomial lower bound with Neeraj and Ramprasad. And for the third one, this paper by Efremenko, Landsberg, and Schenk and Weyman, I think Ketan was referring to this paper yesterday in one talk. Yeah. So this seemed to be giving some evidence that this is not possible, but it's not very clear to me. So that's why this question marks. So it's not too clear to me. So I think I would end here. In my next subsequent talk, I'll try to talk about more limitations of shifted partial and how we can get around in some cases. Okay, thank you.